This talks about basic Lisp for Bitcoin, which is BLL, and also its associated little helper things, which are symbol and bullish. Okay. What? Okay, that's weird. Apparently, I don't know how to use presentation tools these days, but whatever. I hope you all like my OpenOffice template, LibreOffice template. Okay, so what's BLL? The basic two things to get out of this, if you get nothing else, is that BLL is a little language-like script that adds in two things, one of which is looping, which obviously script doesn't have, and the other thing is structured data, which script has only in the very limited way of having two stacks. And the idea is that BLL is the simplest possible thing that adds both of those to script. And so the the way that it adds those two things is basically just a single opcode that lets you do recursion, which is an op-eval-like thing, and you do structured data just by having pairs of objects. And obviously the base object is a byte vector. You can have pairs of those, you can have pairs of pairs, so on recursively. Okay. Symbol is a slight variation on BLL that makes it easier to program. Obviously, if you only have one opcode that lets you do loops and is meant to let you do function calls and everything else, that gets really awkward. So symbol is a way of programming slightly more that's slightly more pleasant than like getting down to essentially raw bytecode. It's got very few different features than BLL. So it's got name symbols, it's got named functions, it's got a short circuiting if macro, and it's got a printf debugging thing. It is interpreted directly. It's not so when you are in BLL, when you're in bullish and trying to do some symbol coding, the symbol code is interpreted directly, so you debug through it as it's written. It's not like the C++ macros or C macros where your code gets changed to the underlying C before you can actually execute it, which makes it a little bit easier to follow what's going on. Okay, and bullish is the third thing. It's just a REPL for BLL and symbol. It has a step-through debugger for both of them, and it has a compiler for symbol down to BLL. It just has a handful of commands, so there's evaluate an expression, define some symbol functions, give some TX data for any of the opcodes that are going to operate on TX data, so like checksig. It allows you to initiate debugging on an expression in either symbol or BLL. It allows you to step through at the same level, continue to the end of the evaluation, or trace through to the end of the evaluation, and it lets you compile a symbol program into BLL. So what's the point of all this? I think there are two main points. So one is that writing code in script is a lot of hassle, as anyone who's enjoyed miniscript will tell you, I guess. And I think so, like the What's Plus implementation in the Great Script Restoration, I thought was a good example. The script code for that that's generated from the lean4 stuff is about 22 kilobytes of script beyond. So there's about 2 kilobytes of pub key data in there, but the other 20 kilobytes is all just all the ifs and SHA-256 and other opcodes to actually implement the logic. And doing that in BLL reduces the script overhead by about a factor of 10, just because you've got access to a looping function, basically. And the other benefit of it is that as someone who wants new features in Bitcoin wallets or in Lightning implementations or L2s or whatever, one of the difficulties with that now is that every single feature for that needs a new soft fork or a new consensus change to do it. So having more features in the scripting language lets you do that sort of thing directly in the scripting language without needing a soft fork. You might still want a soft fork in order to make it cheaper or more efficient or easier to write so that you don't have every transaction having an entire script when you could have it down to one opcode. But being able to do it first and prove the concept, I think, is kind of a win. So I've put AnyPrev out and GraphRoot as examples there of features that you could do directly without much complication at all with BLL as it stands as a concept today. And so, like, the idea there is that's kind of permissionless innovation. You can, if you've got ideas for things you want to do in Bitcoin, you can just write wallet software to do it. You don't have to get a consensus change written up and convince everyone that it's a good idea and go to miners to get them to activate it, go to core and get them to merge it. You still have to do that once to get BLL in there. And you may have future changes to BLL that want to do that, but it reduces those are much it reduces it to much bigger, less frequent sort of steps. So that's kind of my theory anyway. So what are the details of things that I've got in BLL? So the first thing, I guess, is that a lot of the opcodes are generalized. So instead of, like, it goes back to Satoshi's original idea and has big num support, because it's all Lisp-ish, instead of opcodes that have a defined number of arguments they pull from the stack, pretty much everything just operates on a list of things. So instead of add taking 2 arguments, add will just add all the things that are in the list. It re-enables a bunch of opcodes essentially. So it's got cat, it's got multiply. It also adds a bunch of new general functions. So it has BIP340 verify, so check sig from stack essentially. It has the direct TX message calculation from BIP342 that is what is signed in a TypeScript check sig operation. It's got optx equivalent, so that will let you access all the various bits of information about your transaction that's being verified, as well as the prev out that's being spent, in annex data, all that sort of stuff. It has a ECC mollat operation, so each of its arguments are a scalar and a point, and it will multiply the point by the scalar, add all of the arguments together, and expect the result to be the point at infinity. So that's the sort of thing that would let you, if BIP340 wasn't already in consensus, it would let you implement BIP340 directly in BLL code, and also allow for future upgrades, which isn't actually implemented, which is the soft fork operation. So a natural part of this is that you need some way to limit all these things. So if you've got a recursion operator, you obviously don't want infinite recursion that just has your computer sit and spin and never finish validating a transaction. And the way that I'm looking at that is that, first of all, each opcode has some associated cost with it, which is hopefully proportional to the execution time. Might depend on its arguments. So adding 2 numbers just depends on the length of the 2 arguments, and you can just sum them together. Multiplying 3 arguments is more expensive than that because you can be doubling the size of the result at each multiplication, sort of thing. Rusty's already done a bunch of that sort of calculation stuff for the Great Script Restoration project. This is exactly the same as that. The other thing is the total object allocation pool is limited. So when we're looking at these BLL objects, the pairs of things, there is essentially an allocation pool that all of those get put into. Total size of that is limited explicitly. That's different to the way that Chia does things, which only has the cost for the computation essentially. one of the things that this kind of means is that if you want to be able to do expensive computation in a loop, and the loop is short but the computation is long, you want to be able to say that, okay, this transaction is going to take a while to validate. That's going to mean it costs more, treat it as if it weighs more, and then that can just feed back through the regular fee weight calculations. If we didn't have a special way of doing that, then you could just spam extra data into the transaction like the lot of zeros, which would also be fine-ish, but kind of silly. So the computation model, I think, is kind of interesting. Obviously, you want the computation model to be well-defined because it's consensus, so you can't have some implementation saying that, oh, I've calculated it this way, I came up with this value for the cost, and that's fine, while another one says, oh, I calculated it a different way, the cost is much more, therefore the block's too heavy and the block's invalid. So all of this, like the order in which everything's calculated, the order of which objects in the allocation pool are created and freed, all of that needs to be well defined. Obviously, at the moment, it's only defined by the Python code. And the other thing is that it needs to be efficient. So one of the things that might be interesting to do with some of the big num maths is implement your own ECC curve. Maybe that would make sense for some sort of, like maybe there's some complicated post-quantum stuff that actually uses maths instead of just hashing, which you could therefore implement in BLL and do some of the more clever stuff than you can currently do just with hashing. But in order to do that, you want that to be as efficient as it can be, otherwise it just won't work. And so the way I've been working towards that is the evaluation logic is what's called continuation parsing style. I had to get ChatGPT to teach me that. It is absolutely awesome. I don't know if non-Lisp people have ever heard of it. It made it incredibly easy to go from code that evaluates the expression to code that allows you to debug and step through the expression. And in more complicated things, it would allow you to do exceptions and restarting exceptions and other awesome stuff. I'm just amazed by it. Falling out of that is essentially tail recursion elimination, which makes looping by recursion actually efficient and workable. The way the code that I've written is all doing allocation and freeing by reference counting with the proviso that there are no self-referential structures, so there's no way to create a self-referential structure in BLL. There's a fairly small number of opcodes, so there's fewer opcodes than are in Bitcoin, even though it's more expressive than what's in Bitcoin. And there's a very small number of macros which behave in a fancier way than just regular opcodes do. So I'm hoping that all that is going to make re-implementing this in C++ relatively straightforward. Fingers crossed. One thing that it doesn't really have is opcodes for stack manipulation. So script has about 19 opcodes for that. So rot and roll and drop and to drop and whatever else. BLL has maybe 5 opcodes for it. So take the head of a list, take the tail of a list, check if something is a list, construct a list, and construct a binary tree. But it uses the Chia's and kind of essentially simplicity's way of deconstructing a tree of paired objects just by using an integer, so like an integer to access it. So essentially the idea is that you take a positive number, look at it in its binary form, take the zeros and ones and use that to go left or right down the tree until you kind of finish the number. And at that point, you just take the subtree. It's pretty cool and it gives you a lot of power. Okay. So some of the things to think about this at kind of the, is this a good idea level rather than the does it work at all level. I'm going to go through each of these. So one of the things when you have much more powerful a much more powerful programming language on the blockchain is whether you're using the blockchain for computation versus verification. So like there are ideas of playing Doom on the blockchain or using the blockchain to calculate, I don't know, new medicines or new drugs or whatever. As far as I'm concerned, the only real thing that makes sense is using stuff for verification. So there's a Satoshi quote on point for that, which is about treating this as a predicate rather than a program. So the only result you're going to get is a 0 or a 1. And if you got a 0, it's not valid on the blockchain anyway. So really the only result you'll ever get is a 1. Kind of on a similar point to that, is the question of Turing completeness. I think the main, I meant to get a Greg Maxwell quote about Turing completeness being a bad idea, but I apparently missed that. So I think the main thing about Turing completeness is that you're concerned about whether a program in a Turing complete language even terminates. That is addressed here by having the limits on scripts, the limits based on transaction weight. So you can run a transaction until it uses up the computation that's implied by its transaction weight. Then it doesn't matter what the logic of the script is, it definitely terminates at that point. So in that sense, it's not Turing complete. And in a more trivial sense, it's also not Turing complete because script sizes are bounded, but whatever. So simplicity has a slightly different concept, which I don't fully understand. I haven't studied it properly, but is finitary completeness, I believe. And I think the idea there is that it gives you a strict bound on execution size based on the program passing the type checker. And passing the type checker is easier and faster than actually doing the execution. I am not aware of that bringing any extra benefits apart from being cool, beyond just actually saying, if you execute this program, it will take no more than whatever time. But I think you already get the same thing just by saying, I'm not going to execute this any longer than however large the transaction was in the first place. So this set of slides goes on for a bit, and the idea is that maybe these new features enable people to do bad things of various types. So does it allow new types of spam? Possibly, but the spam is any spam that comes through is all pretty much under the same limits as the current chain. It definitely does let you construct covenants. So you can say, this transaction is only valid if the output has the same value and script pub key as the input that's being spent, or more complicated covenants than that. Those are a bad idea, but obviously you define the script pub key that you're going to accept payments to, and as far as I'm concerned, it makes sense to just let others burn their funds if they want. They can already do that with burn addresses that move their funds to other chains if they want. So like the space chain one-way peg, for example. Obviously, if you are able to do your own ECC calculations directly, that's essentially write your own cryptography, and that is oftentimes a very bad idea. So it makes it at least possible to create very unsafe wallet software. That might mean that if you're going to say, oh, this new software, the new wallet is just for Bitcoin, that's not as trustworthy as a wallet that claims to be just for Bitcoin is today. So one of the other things is that you can put other assets on Bitcoin's blockchain and maybe trace them through in a better way than what ordinals or inscriptions allows you to do. as far as I appreciate the threat is the threat that actually means is that all the activity that would be being performed on those assets, so real estate or stocks and exchanges and whatever, options, whatever, all of that stuff would be more valuable to the people using it than actually making BTC payments is to Bitcoiners, and that would push BTC out of the Bitcoin blockchain, which would obviously suck. I've kind of put some reasons why I'm not too concerned about that, but that I think is a valid concern. I'm personally more on the hope that this sort of thing would allow us to put BTC off of the Bitcoin blockchain, so transfer it to side chains and whatever in more decentralized or more secure ways than we currently have. But that's a research problem, kind of. So, and obviously there's always the scary MEV stuff. So I think the MEV question is very much a wallet question in the sense that you define a script that allows funds to be transferred here and there. You define an authorization that satisfies a script that moves the money from you to someone else or from someone else to you. But the hope and idea is that those authorizations will be strict enough so that it doesn't matter how hostile or clever or whatever someone else on the Bitcoin blockchain or peer-to-peer network is, they can't manipulate that authorization to make you lose money. As far as I'm concerned, if they can do that, which is where you get MEV from, that is a bug in the wallet, and hopefully the language is powerful, efficient, straightforward enough that you can code wallet software in a way that just doesn't happen. But I think that's much more of a question of let's write some software in it and see how it works out rather than try and make it impossible from the get-go. I don't know. And so yeah, I think much of this point is just the other side of the permissionless innovation mirror. Like if you don't need to have permission to innovate, then people are going to do bad things. So suck it up. I don't know. And the other philosophical sort of question is whether we want Bitcoin to be providing opcodes that do special cases really well, or if we want to have opcodes that provide general features really well. So like that's very much one of the questions from the opvault BIP, and Vault tries to provide a very special case, tries to provide opcodes that are very honed to solve a special case very well and maybe do other things generally, but mostly focus on that special case. And how much we want to focus on one of those versus the other, I think, is an open question. Obviously, BLL focuses very hard on the general case. So yeah, that's some points and example kind of for that. But I think like that's a very high level sort of question that, I mean, the only way you might get some answers from that is having a lot of demos and experiments to get some experience with, as far as I can see. But I think it's a valid question. Okay, so as far as I'm concerned, that's my to-do list. So the flexible earmark post on delving was the theory that I want to satisfy, and I think I've got an idea of how to write that up in symbll now that I think is not too complicated, but I haven't done it yet, so that's what's top of the list. The other thing I haven't done is actually define what result from a BLL expression is the success condition. All of them seem a little bit odd, so I'm probably going to just go with anything that's not an error at this point. as opposed to scripts, anything that's not falsy. So yeah, after that is the rewrite to C++ and the attempt to merge into Inquisition and make it usable. And maybe at the bottom of the list is get a formal specification implemented in Lean 4 and do some formal verification sort of stuff. And I think that's the planned part of the talk, and hopefully there's plenty of time for questions. Yep, great. Okay.
How much of the upside to like the proposals that are being discussed right now, would you say is attributed to looping being added? Like, I mean, there's a whole lot of other stuff that is going on with the proposal, of course, but like you named as an example of like the Watts example and how that would be improved with looping, and like how much would you say is like the looping actually like the I guess the killer feature of your proposal versus the other stuff?
So for the Watts example specifically, there were two things that made that difficult. The script size is pretty much 100% the looping thing because every opcode that's every operation that's doing work in the Watts plus stuff is executed, I think, 64 times, so once for each pub key, and each of those are executed 16 times, or on average 8 times, but up to 16 times for each of the verification steps in the pub key, and that multiply those together, and that's pretty much the difference between the two script sizes. But the other thing in actually, so the way that the GSR Watts Plus script is created is that it's generated from Lean 4 implementation. So you write out the spec in Lean 4, which has loops and all sorts of all sorts of powerful features and stuff, and that generates the script code. And so that lets you do the looping without having to write these things out yourself 50 times each. But to actually do that, you need to keep track of the stack and manage that and do all the stack operations. And that doesn't really use up that much space in script, but it's very complicated to follow. So, I mean, I don't know how you'd measure that, but I think that's also a big benefit. So I think there was a post on Bitcoin Dev the other day about the op success opcodes, and WK wanted to be able to have okay, this is all fine now. We've found the problem. We've found the problem with the proof that was published. Therefore, the other guy gets the complainer gets all the funds. And he wanted to have an opcode that would just abandon all the work that was on the stack because it's all done now. But because that could happen at various points, he didn't want to have to unwind the stack. Because obviously currently the stacks, the transaction's only valid if there's only a single non-zero, non-falsy value on the stack, not many values of which the last one is non-falsy. So I think there's a fair bit of that sort of thing for complicated scripts.
Stefan?
Yeah, I think two questions. I think they're somewhat related, so I'll just phrase them at the same time, but feel free to split them up into if that makes more sense. I guess in terms of, positioning bullish or, any of the key concepts next to some other projects like GSR and simplicity, it sounds to me like this is a strict superset pretty much of GSR in that it does add all the functionality GSR would include, as well as like the budget for each operation to make sure that we don't make things more complex. That's the first question, like about GSR. Is this indeed like roughly a strict 2%? And then the second question is compared to some, for example, simplicity. What are the trade-offs that you're actively trying to make compared to simplicity? It sounds like you're trying to add similar levels of expressivity as simplicity, but then in a way that actually might be mergeable, as opposed to simplicity becoming such a big project because of its provable correctness and all those concepts.
So GSR, it should be a strict superset. Everything you do in GSR, you should be able to do in this. And if not, it should just be a matter of adding a missing opcode. So when I did the what's plus thing in BLL, I had to add the shift opcodes that I hadn't implemented yet. There may well be more stuff like that, but that's a bug, not anything deliberate or very interesting. I don't believe implementing the opcodes in BLL should be any harder than implementing them in GSR. And yeah, the bound work should be exactly the same. Obviously, I haven't done anything on that because it would just be evaluating how long it takes to do calculations in Python, which I don't think is entirely relevant. As far as simplicity goes, there are two things I think that made me look at this instead of just focusing on simplicity. One is that the equivalent of the opcodes that BLL has in simplicity are jets. So jets are various bits of functionality that are initially specified in very basic simplicity instruction terms, but are then bundled up, given a jet number, implemented in C++, and then just made available at a cheaper rate than it would be, like a cheaper execution price, essentially, than it would be if you were implementing them directly in simplicity. There are a lot of jets needed to make simplicity work. So, for instance, where I've got a SHA-256 opcode in BLL, there are, I think, 3 opcodes in simplicity to do that. So there's initialize the SHA-256 calculation, add some data to the SHA-256 calculation, and finalize the SHA-256 calculation, which is fine. I mean, that's how the SHA-256 calculation is implemented in Bitcoin in C++. But because each of those jets have a simplicity result rather than just being internal things, it means they're not the exact same implementation. So like there is specific C++ code for that, which I think it makes it daunting to review at the very least. And I'm hoping that BLL and C++ will be simpler, but until it's done, I don't know if that will actually turn out that way. The second thing was that I think the original hope, inspiration, whatever for jets was that because the code, like the jet code is specified in simplicity first. So the original hope was that you'd be able to say, oh, here's some code that I've written in simplicity and everyone's going to want to use it. And we can just let everyone use it in a fairly cheap way in future without having to respecify it because they can just use the jet 32-byte encoding for it. And as far as and that hasn't panned out. Like to do a new jet, you have to do a consensus update because it makes the code cheaper than specifying it fully in simplicity, and making things cheaper is a hard fork if you just do it, and a soft fork if you do it via some new thing. And so if that had worked, that would have definitely justified having all the complexity in jets because it would just be underlying simplicity and some magic. But since that hasn't paid out, I think trying to simplify the jet concept is worthwhile, and hopefully that'll work, but we'll see. I guess the other thing is that simplicity has Symfony now, which is like the symbol thing, so it's the nicer front end for programming. So that is also very parallel.
Sebastian?
Yeah, I was wondering, you mentioned the macros. Is this purely a thing that is convenience for the user, so only relevant in symbol? Or would the Lisp consensus engine still be aware of macros?
So the way I used macros on this slide is that it the opcodes behave in a really regular, normal way. The macros behave specially. So when you're doing plus of times of 2 and 3, or if you're doing plus of times of 3, 2, close bracket, 1, close bracket, you'd do the multiplication first, and then you'd add 1 to it, right? With the Q macro here, you don't evaluate its arguments. You just return them directly, which is a standard useful feature of Lisp. But it's and it works really lovely with the continuation passing style of evaluation. But it's a difference of kind between the opcodes, and in Lisp it's commonly called a macro to do things like that. So I've kind of adopted it here. So A does tail recursion elimination and returns essentially a program that starts getting evaluated, as opposed to a value that is just a value. Q returns its argument unevaluated. Partial takes a partially evaluated opcode, adds an argument to it, but doesn't finish it. And soft fork's not implemented yet. So those ones are in BLL. They do special things. At some level, they're just opcodes, but they treat their arguments or treat their return value quite differently to every other opcode. So I'm treating them special in that way. The opcodes in symbol, so report and if, both are special as well. They don't show up in BLL, like they get translated to A and I and stuff.
Another question, I was wondering how complex is the serialization of such a BLL program? Because in script, it's really simple, right? You have a 1-byte opcode and data, and here you can do stuff with nested lists. So I figure this must be a little bit more complex to come up with a good serialization format that is also not wasting the space too much.
Yeah, so I did come up with a really complicated serialization format. And then when I rewrote the BTC list to BLL and into continuation passing style, that broke everything because I changed the way everything worked. And instead of fixing that, I implemented the Chia serialization format. And the Chia serialization format is really simple. It's got it's byte oriented still. It has a byte that indicates, okay, I'm going to give you a pair next, so you'll get one value and then you'll get another value. And other than pairs, the only other thing is byte strings. And so the byte string starts with a size, which is is basically like compact encoding. So it gives you the size and then it gives you the data. And that's not terribly efficient because every list in these things is a whole bunch of pairs, which means instead of saying I've got a list of 20 items in my expression where you might say list 20 and have that be 2 bytes, you've got 20 bytes to start a pair each time, which I thought was a bit inefficient, and that's why I tried making a more complex thing. And I haven't made that work again yet. So all my current examples of serializations have been in the Chia Lisp serialization, which is a little bit bloated, but I mean, it's still not bad. Did that actually answer your question?
Yes, thanks. I was just wondering if there is already a serialization format and how it looks like.
Yeah, so I've got some examples of serialization in some of my delving posts, which I mean, you need to go into BLLSH and decode them to get any meaning from them, but you can get a sense of how large the serialization is.
AJ, you mentioned that it's possible to implement new features without a soft fork, and you gave the example of APO and graph root. You also noted, I think, that there could be a reason for cheapness or efficiency to add in additional custom opcodes and future changes to BLL. Can you give me an idea of what the types of things that people are talking about today implementing for Bitcoin covenants, Bitcoin script? Like what's the delta there? Like what would you anticipate would need to be added in the near term?
So I think the What's Plus thing is a good example. So the What's Plus script has about 2 kilobytes of pub key data. So I mean that is obviously different for every single pub key, but the GSR style one would leave 20 kilobytes, and the BLL style one would still leave like 1.6 kilobytes of actual code. That 1.6 kilobytes could be reduced to a single 1 byte opcode if you were soft forking that in, because everyone was doing it all the time. And when you soft forked it in, that would give you a chance to write the implementation in C++, make it more efficient, do some precise calculations, benchmarks on it, and give it maybe a cheaper cost than it had when you specified it fully directly. So like that's a relatively big saving, I guess. 1.6 out of 5.6 kilobytes. The like doing Ccache any prev out versus specifying it in BLL, I think would be a lot smaller. So in the BLL, in the bullish repository, I've got some examples, one of which is a re-implementation of Ccache all directly in symbol/BLL. And if I just run that now, maybe. Okay, so doing Ccache all evaluation directly in BLL, so Ccache any prev out validates less stuff, so it would be a little bit shorter, is about 550 witness bytes. I think including the strip pub key, maybe? No, not including the strip pub key. So that's about a that's about a 5 of 5 multisig equivalent to be able to do a feature that would otherwise take a consensus change to implement. And saving a 5 of 5 multisig's worth of fees, that is definitely something people would like if they were doing it all the time. And if they're doing it all the time, then that is probably a good, like if you can already see that on chain that lots of people are doing it, that's probably good evidence that something might be worth a soft fork. If nobody's doing it, then that's probably not worth a soft fork. But yeah, that's the level of difference, I guess. You're saving what, 130 vbytes worth of data in your transactions that are using the feature.
Those are good examples of, using the existing set of opcodes and macros that you've outlined. People can build X, Y, Z, and then if it catches on, you can have a custom opcode that is more efficient or can do some proofing or saves fees. Are there things not in the toolkit that folks are talking about building, like the CTV, TX hash kind of things? Like, are the building blocks there to build something like that, for example?
Yeah, so there like the concept space of things that you could build in Bitcoin is probably infinite, and trying to work out which one of those you're not thinking about because they don't make sense, and which ones you're not thinking about because they're too hard in script is a little bit tricky. So like the the flexible earmark stuff is essentially my new take on tap leaf update verify, and tap leaf update verify really kind of doesn't entirely make sense in the context it was because the taproot commitment doesn't include the sign byte of the internal public key and how it was generated, and that isn't necessary for taproot things, but for the kind of stuff that tapleaf update verify would be useful for, it is necessary for, and there just wasn't really any sensible way to store that. But when you have more flexible features, more flexible programming features, you can find places to store that, store it there, and then use it. And so that's one of the things the flexible earmark stuff is trying to do. And that in turn can then be used for things like hopefully better L2, which we talked about a little bit in the I talked about in the flexible earmarks delving post and a bit more on the OpTech podcast, which is now out as I understand it. I consider that stuff speculative. I'm pretty confident that there is more fancy stuff that you can do with these general languages than you can do with the specific opcodes that are being discussed. And I think you can do it more conveniently because you can specify loops and things.
AJ, what would be valuable from this group or the folks who might be listening or watching this video to do to help test or contribute to your effort if they're curious about it?
Have a play with the bllsh, with the bllsh REPL. Have a read through of the flexible earmarks post and see if that makes sense or if it's even understandable, I guess. I know Merch didn't really grok it on first read, so maybe that's a big ask. Yeah, otherwise, any questions are great. Any interest is always great. If there are a few examples in the repository for Bullish, if you read through them and have any questions, that's great. If you want to try your own experiments with it, that's also interesting. Yeah, otherwise, that's my to-do list. So if you want to help with any of those things, then I guess that there are issues and pull requests on the repo that you could open.